Hello everyone. So we'll start with week 9 session. Okay, so I hope you guys have seen the video lectures on centrifugal compressors. So I'll just quickly go through what are the different parts and what is the working principle of a centrifugal compressor, and I would request you to please help me out here. Okay, so what are the most important parts in a centrifugal compressor? You can see this diagram on the screen. Yeah, guys, just speak up, please. Yeah, yeah. What is the work of an impeller? So we can see there is an impeller here. It will add kinetic energy, right? So it is essentially like a rotor, right? Impeller is nothing but the rotor, and this is the rotating part of your centrifugal compressor. Okay, and then what is the next important thing? The diffuser, right? So what is the job of a diffuser? It will convert the kinetic energy into pressure energy. Okay, so basically what happens, this is what you can see, the first diagram, that is the side view, right? And this is the front view. And what happens is that air is taken in along the axial direction, and the flow is completely converted from axial to radial direction. Okay, and in this process, first the air undergoes rotation in the impeller section, and then in the diffuser veins you can see, like for example, if you concentrate on this vein and then this vein, you can see that the area is increasing. So the flow velocity is going to decrease, and basically the kinetic energy will decrease and the pressure energy is going to increase. But in the impeller, the kinetic energy is increasing. So what is happening to the pressure energy? Can you tell me? Is the pressure energy increasing or decreasing? Yeah, so if I just, for example, if I draw the pressure along this radial direction, right? So this is your radial direction, and say up till here is your impeller, and after that is your diffuser, right? So up till here is the impeller, and then beyond that is the diffuser. So I'm asking what happens to pressure and velocity. So velocity is clear. Velocity is increasing in the impeller, and then it is decreasing in the diffuser, right? Is this part clear? Yeah, so what about pressure? What happens to pressure in the impeller? And in the diffuser, you said, right, that pressure energy is increasing. So pressure is increasing in the diffuser. What happens to pressure in the impeller? What is the work of a compressor? Yeah, so what is going to happen in the impeller? Yeah, pressure will also increase, but now I think you are confused. Yeah, because the kinetic energy is also increasing and pressure energy is also increasing, right? So how is this possible? So the thing is, if you see in the rotating frame, if you basically sit on any one of the impeller fans, then you will see that the relative kinetic energy is decreasing. Okay, so you are adding work over here. You're adding work from outside to the rotator blades, and that is why it is able to increase both kinetic energy and pressure energy. In the diffuser, you are not adding any work, so something has to decrease to increase the pressure. That is why the kinetic energy will decrease in the diffuser. But in the impeller, you are anyways adding work, so that will go in increasing the kinetic energy and also in increasing the pressure energy. And why do you need to increase the kinetic energy in the impeller? So that once it exits the impeller, the kinetic energy will decrease dramatically in the diffuser and hence increase the pressure energy further. Okay, is this part clear? Yeah. Okay, so if we just summarize the working, so I'll just maybe keep, yeah. This is static pressure. So what happens to the total pressure in the impeller? What will happen to the total pressure? Yeah, total pressure should increase in the impeller, and in the diffuser, yeah, it will remain constant because we are not adding work, or we are assuming there is no heat loss. So the stagnation pressure or the total pressure will remain constant in the diffuser, but it will increase in the impeller. Okay. Okay, so and then what is this thing called volute? What is the purpose of volute? So this white color thing which you see over here, this is called a volute. Yeah, you can see that somewhat the area is increasing along the tangential direction, right? So once the air comes into this volute structure, again the area is increasing slightly to increase the pressure further. And also the purpose is to kind of store the air here and give it the right direction. So for example, if you have another stage of the centrifugal compressor, then you can just direct the air from here to the next stage, right? So that is the purpose of a volute. Okay. Now you must have also seen in the lectures that the design of these impeller blades is very important. So whether they are radial or forward lean or backward lean, so we'll discuss that in one of the coming questions. Yeah, okay, before we go on to the questions, I just want to summarize the uh, entire process. So the first thing that happens is you have air coming into the air from inlet, right? That goes into the impeller where work is being added. I mean, you would be having some turbine which is running your centrifugal compressor. So work is being added here. Then what happens? What happens once the air is directed to the impeller? So from what direction does the air move inside the impeller? Do you have any idea? So for example, you see that the impeller starts somewhere over here, right? How does the air come and hit the impeller, and how is it directed? So obviously the air has to go from impeller to diffuser, so it is going to move in this direction, radially outwards, right? But when the air is being taken in, is it taken radially inwards or outwards or axially? How is it taken? Okay, it hits axially, but it hits axially around all radial positions, right? And it does not hit just at the center, but you have to move the air from the center to outwards. So how do you do that? So there is air coming axially and it is hitting this entire surface. So then how do we basically guide the air? Yes, so there is an inlet guide vane, and what the inlet guide vane will do is it will direct the air towards the center. So it will direct all the axial air, I'll write all the axial air uh, towards the center. Okay. Of the impeller. And then because of the rotating action of the impeller, the air will be pushed radially outwards. Okay. So air is pushed outwards, radially outwards. Due to what? Due to what action of the impeller? Centrifugal, yeah, rotating, and that is basically going to cause a centrifugal action. Okay, so centrifugal action of the impeller. Okay, then what happens once the so now the kinetic energy has increased, right? So I can write over here, therefore kinetic energy increases. Then air is pushed into the diffuser vanes. Okay, and in the diffuser vanes, as we discussed, the kinetic energy decreases and the pressure energy increases. Okay, don't confuse this with potential, I mean your pressure. All right, and then finally this from the diffuser vanes, air is collected in volute and it is transferred further to the next stages, right? Okay, so if you understand this entire process, then solving any question or basically visualizing what is happening, that helps you understand all the velocity components. So whether the flow is in the axial direction or the radial direction, and also in the tangential direction, because if you just consider one blade, for example, say this is the blade, so along this blade the air is going to be pushed like this outwards, and then it is going to turn around, right? So it is also going to have an axial the tangential component also. So all these velocity components will come into picture when we draw the velocity triangles. Okay, so now you can answer the questions. First question is, centrifugal compressor is mainly preferred for what type of pressure ratios or what type of applications? What is the answer here? Low volume flow rate, yeah. But okay, we also get very low pressure from centrifugal compressor or very high pressure. So if I compare for example, if I compare the pressure ratio for a centrifugal compressor and an axial compressor, so which one has higher pressure ratio for one stage? Yeah, any idea? For once, if I just consider one stage of a centrifugal compressor and one stage of an axial compressor, which one has more pressure ratio per stage? Okay, so it is the centrifugal compressor. Okay, reason being that in the centrifugal compressor it is a low volume flow rate application, and in axial compressor you have to maintain the axial flow, so you cannot change the pressure basically, because you cannot change the direction or you cannot really slow down the flow dramatically. You need a high volume flow rate like in a turbojet engine, right? So you need the flow to be moving through different stages. You don't want to slow down the flow rate, you want to keep the velocity almost constant. So in an axial compressor, what you'll see is that there is a rotor stage, there is a stator stage. You will say increase the velocity in rotor and then you will decrease the velocity in stator in an equivalent manner, so that on an average the velocity will remain same. Okay, so you want to keep the volume flow rate constant throughout the axial compressor. So as a result, what will happen is that in one stage the increase in pressure is much smaller for this axial case, but for the centrifugal compressor, within one stage you have much higher pressure ratios. And that is also a reason why you don't really go for multi-staging in centrifugal compressors. Okay, Okay, then the next question is the presence of inlet guide vanes in a centrifugal compressor leads, it is responsible for doing what to the relative velocity? So, what is the answer here? No. So, see, the inlet guide vane is like you said, it is going to guide the air from all the locations. So, coming back to this diagram, from all the locations, it is going to guide it towards the center, right? If you see more carefully, sometimes the inlet guide vane is like this. I'll probably draw it. So, this is the impeller blade, and you have to imagine in 3D that there is a guiding structure over here. So the flow is forced in this direction, so it moves towards the center, and then by centrifugal action only the air will be pushed outwards, right? So in the process of bringing the air towards the center, the energy which is lost is the kinetic energy, right? So it should decrease the relative velocity. Do you understand? Yeah, okay. Okay, so now I have given here the expression for work done for a centrifugal compressor. So this you must have seen in lectures. You can just quickly tell me what are these variables A, beta 2, U2 and so on. A is the flow coefficient, okay. What is U2? Beta 2 is the blade velocity or the blade angle? Okay, U2 is, yeah, sorry, it's the blade velocity. Yes, exactly. So this is the blade angle. Okay. Okay, now which of the following option is correct for the pressure coefficient, which is nothing but the stage loading coefficient for a centrifugal compressor with radial vanes? So what happens in a radial vane? What is a radial vane? Remember, if you go back to this diagram, this diagram has impeller blades which are radial along the radius, right? They are not bending. They are not bending like this or like this, right? So this is called radial vanes. So what happens to the pressure coefficient here? Yeah, and it is equal to 1, right? So the answer here is 1. But what happens if we have a forward lean or a backward lean, which we'll discuss subsequently? So, okay, I'll just draw this. This is for the radial case. Okay, but if I basically change the radial velocity, then you will see that in the case of forward lean, the stage loading coefficient increases along the radius of the impeller. So as you move outwards, radially outwards, you'll see that the stage loading coefficient is increasing, right? And in the backward case, it will be decreasing. So this is backward. Okay. Alright, so then next is for the given expression of slip factor of the centrifugal compressor, identify the right option for alphabet C. So what is alphabet C here? What is slip factor basically? Okay, this is a simple question. How do you define slip factor? Yeah, tangential component upon blade velocity. So what is the answer from here? Question 5. If you see the options, tangential velocity is also called the A whirl component, right? Okay, so A is the answer. All right. Question 6. The ratio of relative velocity to blade speed of the centrifugal compressor is defined as. So, relative velocity to the blade speed, that is W, divided by. Yes, right, it's flow coefficient. So, this is what also came up in your expression of work right now, right? This A. So, that is the definition here. Okay. In the absence of inlet guide vanes for a centrifugal compressor, the flow enters into the inducer of the impeller with the absolute velocity angle of. What is the angle with which the air hits the impeller blades? So, what is the purpose of an inlet guide vane? That is to adjust the angle, right? Now we are saying there is no inlet guide vane. Then how will the flow enter into the inducer in the impeller? Yes, axially. So it is going to be at 90 degrees, right? So the answer is A over here. Question 7. Okay. Then centrifugal compressor with a backward vane leads to outlet blade angles of the impeller which are more than or less than or equal to 90 degree. Okay, so maybe we can discuss question 8 after discussing question 9. So, do you know how the impeller blades look in the case of forward and backward vane type? So, radial, it's obvious. The blades are basically going to be along the radial direction, right? So, can you tell me how it is for a forward vane type? So, what do we mean by forward or backward? So, say for example, I can rotate this impeller system anti-clockwise. I could have also rotated it clockwise. It doesn't matter, right? Do you understand what I'm saying? Yeah, because the blades are in the radial direction. So whether it is anti-clockwise or clockwise doesn't matter. But now if I twist the blades, right? So let us say that we are going to rotate anti-clockwise, and the twist of the blades is such that the twist is in direction. Okay, I'm sorry. The twist is in direction of the rotation, like this. Then this is called a forward lean, because the twist of the blades is along, I mean, it is in the forward direction. Forward as in the direction in which the rotation is happening. So this twist is what is defined as the forward or the backward thing. So now it is very obvious that if say we were rotating anti-clockwise, then what is backward lean? If your twist is such that it is opposite to the direction of your rotation, right? So this is the backward lean blades. Have you seen this before? Yeah. Okay. So now can we draw the velocity triangles? Let us start with a simple thing, which is your radial velocity. So first there is one radially outwards velocity, right? So let us call that W. And then there is a tangential component, which is, so at this radial location it will be U. Okay, you can call it U2 or W2. And then the vector sum of this is C2, right? And in the case of a backward lean, so if I just consider this blade for example, then how is W going to be? What is W basically? It is the velocity along the impeller blade, right? So here the air is going to come out radially. Here the air is going to come out in this direction along the impeller blade. Is this clear? Yeah, tangential to the blade. but it is called the radial component. So this is called W. And of course you are still rotating in the anti-clockwise, so the velocity component u2 is still going to be leftwards like this. That depends on your direction of rotation, right? And then this is your c2. And in the case of forward lean again, so now you can draw w in this direction because, as you said, tangential to the blade. Okay, and because you're rotating again in the anti-clockwise direction, your u2 remains in this manner. Okay, this is w2, and the vector sum is c2, right? So I hope the velocity triangles are clear over here for all the three vane types. Yeah, okay. Okay, so now we can get back to question 8. So centrifugal compressor with a backward vane, which is this figure, it leads to an outlet blade angle of the impeller which is less than 90 degree. Okay. Okay. Okay, then I have one last question. Define the slip factor. So we have done this already, but I just wanted to give you some more information. So the slip factor over here is defined as so if you come back to this question, it is the whirl component by the blade speed. And what is the whirl component actually? So let us take the case of a radial centrifugal compressor. So the whirl component is the tangential component. So this is C2's tangential component, right? So if this is the angle theta, then I'm talking about C2 sine theta. Okay, and I will denote that as C2 theta, and this divided by the blade velocity u. Is this clear? Yeah. Okay, so now what happens is that ideally, like, okay, let me just copy paste this figure. Okay, so this is the ideal situation, right? But what happens is that you expect that the flow is going to come out radially. That is because it is going to come out along the impeller blade. But if it does not come out along the impeller blade, and basically there is some slip that is due to lack of enough friction, or there is some inertia in the air, it was supposed to be in this direction, but it turns out that it moves slightly in the other direction, right? So then what will happen? So if I draw the velocity triangle separately over here, it was supposed to be in this direction, but the air slips and moves a little in the opposite direction of the rotation because of some inertia, and your u component is like this, and this is your c component, right? So now if you see, in the ideal situation, c2 theta was supposed to be equal to u2, but here you will find that c theta is actually less than u. And to quantify this slip, this change in direction, we define this slip factor. Okay, so I hope the definition is clear along with this picture. Okay, so do you guys have any questions to ask? Because that's all I have for today. What is the function of? Yeah. So that is actually that's what I was actually trying to explain, that the air, so you are supposed to take the air in the axial direction, right? And then it is supposed to move in the radial direction. So inducer is nothing but it is like a guidance to the air. But so ideally what do I want? I want all the air to come in a concentrated manner to the central location, so that I can just push it out, and that is the most ideal situation. But that doesn't happen. So okay, inducer is what you will see, that the blade of the impeller will be designed such that it has this very sharp edge. It's cusped and sharp edge. This is the impeller blade. Okay, so this is the inducer. It will, anything which is coming um, in the axial direction, and it is coming from the outside, it will be induced like this, right? So you are seeing the direction in which it is being induced towards the center. So until and unless the centrifugal action is pushing the air outwards, if that is, say there is no rotation, and you just bombard this impeller with air, then this inducer is simply going to guide it towards the center. Are you understanding? Yeah. So the job of the inducer is to ensure that all this air which is coming from the axial flow, it is moved towards the center. Okay. Okay.